Hi, this is Physics 1, Chapter 2, and this will be Part 3. And we left off looking at acceleration, which is the changing of velocity. And it could be due to the speed changing, which is the common way we would think of it. So going from 40 miles per hour, let's say, down to 35 miles per hour. And it could also be due to the direction changing. So for example, moving in a circle. And it could be due to both of these, which can easily happen as well. Alright, so when the distance is changing, the rate at which it is changing is the velocity. When the velocity is changing, the rate at which it is changing is the acceleration. So we want to look at instantaneous acceleration. Which we're going to label A. It's going to be equal to the change in velocity over change in time. A lot of times you may just see this written as A equals V over T. Right. Now, we're going to get more into details with our motion equations as well. But these are for basic, you have basic change in velocity over time change. Right. And then you also have what's called the average acceleration, which we'll label as A with a bar above it, which is equal to your final velocity minus your initial over your final temperature minus your initial temperature, which is usually going to be 0. So we can say that this is the final velocity over initial velocity over a change in time. Now, the units for acceleration, the SI unit is meters per second squared. You can have any other units in terms of a distance per time squared. So you can have something like kilometers per hour squared. You can have meters per hour squared, miles per hour squared. All these can be acceleration units because it's a distance divided by a time squared. Usually we keep the units for the time squared the same units. Okay, so acceleration is going to involve direction since it's also going to be a vector quantity. And so what I'm going to do here is go over two examples with cars and look at how these vectors look depending on the acceleration to help with the direction. So first of all, for this blue car, we're going to look at a car that's speeding up. And so the car is moving to the right. It's speeding up, so its velocity is increasing. And so its acceleration is going to also be to the right. Okay. Here the acceleration is going to be in the same direction as the velocity. So the velocity is also, alright, V here, to the right, and the acceleration is to the right. If the distance and velocity are to the right, then acceleration is positive. If we have instead, let's say this car is in reverse, have velocity going this direction, we're going to call that the negative velocity. So we're backing up, but as we back up, we're speeding up. So we're still increasing the velocity, and then we'll have a negative acceleration. But the key here is your velocity is still increasing. Okay, the fact that we're going in reverse doesn't mean that this car isn't speeding up. They may very well be pushing on the gas and pushing that gas down harder, having that speedometer go up, but they're going in reverse direction, which makes it negative. So when the velocity and acceleration are in the same direction, that's when you have speeding up. And that's when you have what we call, or what we could have a negative acceleration. Now, when a car is slowing down, so we get down to this orange car. Here, the velocity and direction are opposite. So when the velocity is in the positive direction, but it's slowing down, and in this case braking, your acceleration is going to be backwards. So your acceleration is going to be negative. If, let's say, we have the car in reverse. Right. So this car is moving in the negative direction. So you have a negative velocity. But you're braking and you're slowing down still, so you're still braking, and you're looking at a negative, positive acceleration because it's to the right. Right. So when your acceleration and your velocity are opposite, that's when you have slowing down. Right. And so you can have slowing down when the acceleration is positive or when the acceleration is negative, depending on which direction the speed is going. Most of the time, if we can keep the velocity in the positive direction, then we know if it's slowing down, our acceleration is negative. If it's speeding up, our acceleration is positive. That's only if we can keep the acceleration, or the velocity in a positive direction. A lot of times we can make that happen. I guess there may be instances when you get farther into this where that may not end up being the case. And that would have to be when something else is dictating which direction is positive, which direction is negative. Alright, so let's get to an example. We have a sports car accelerates from rest to 95 kilometers per hour. So the velocity goes from 0 to 95 kilometers per hour in 4.3 seconds. Right, so I want to switch this to meters per second first. So 95 kilometers per hour times, let's see, 60 minutes in 1 hour. So this gets the hours cancel. 60 seconds in 1 minute. So this gets the minutes cancel. And then in 1 kilometer, we have 1,000 meters. So that's it's the kilometers cancel. All right, so 95 times 1,000 divided by 3,600. And we get 26.4 meters per second. Right, so the average velocity is going to be equal to the 26.4 minus 0, because it started at 0, over 4.3. So 26.4 over 4.3. And we get 6.14. 6.14 meters per second squared. I prefer to keep those units for acceleration, especially once we get into forces and energy, because we'll just be dealing with those units on a normal basis. Okay, so next one, we have a sports car moving at constant velocity, traveling 120 meters in 5 seconds. So the first leg of the trip is 120 meters, 5 seconds. And then it brakes and comes to a stop in 4 seconds. So at this point, you're braking, and in 4 seconds, it comes to a stop. So velocity equals 0. Right, so along this traveling, the velocity is going to be constant. So at this point, your velocity is 120 meters over 5 seconds, which would be, that's my calculator. It's 24. I just want to do this and make sure. 24, yep. 24 meters per second. Right. And then it's going to brake. And so your acceleration is going to be the 24 meters per second minus 0. Actually, wait. Final minus initial. 0 minus 24 over 4 seconds. So negative 24 over 4, which would be negative 6 meters per second squared. This will be your acceleration when as it starts to brake. Right, so now this part of the question asks how many G's? Well, G is just equal to 9.8 meters per second squared. That's gravity. So we want to know how many G's. We'll take the negative 6 meters per second squared times it by 1 over 9.8 meters per second squared. Well, this will be how many G's? So negative 6 divided by 9.8. And you get negative 0.61 G's. Okay. So now, most of the physics problems we're going to be dealing with are going to be dealing with time. We'll be looking at objects moving over time. Most of the time, the starting points for an object will be considered 0, or we can separate this out into problems where, for instance, up here, we consider this 0 and this to be the 4 seconds. We separate it into 2 different sections of the problem. And we can do that a lot. And it actually breaks it down, makes it a lot easier than trying to do everything all at once. And so most of the time, the starting points for an object is considered time 0. The ending point will be considered the final time. And so displacement and velocities at their starting point will have special symbols, x sub 0 and v sub 0. And a lot of times we'll also, I should include this here, but I'm going to mention it, acceleration will be constant. And a lot of problems we'll be dealing with. So when we get into that, we have specific equations that we're going to be using. And these are actually called kinematics equations. Now the general, and I guess you can say even more complex versions of these are x equals x sub 0 plus v sub 0 t plus 1/2 a t squared. And again, remember, constant acceleration. Okay. And then velocity equals v sub 0 plus a times t. And then a equals a. This is just kind of stating what I just wrote up here, constant acceleration. So these two, I'll label them 1 and 2, are going to be the two main ones dealing with this constant acceleration. If you ever took calculus or pre-calculus, actually you probably won't see in pre-calculus, but in calculus you'll see that this, if you take what's called the derivative of this, you get this, and that's how they relate. If you take the derivative of this, you actually get this. Right, so this can be for any object moving in one dimension. If we're talking about vertical, we may actually just change the unit. So we may say, okay, well, if we're talking about vertical, we'll do y equals y sub 0 plus v sub 0 t plus 1/2 a t squared. Same thing, it's just we use y for up and down, x for left and right. Right? But you don't necessarily need to do that. If you kind of draw a picture and state that up is x, that's fine, as long as it's one dimension. Two dimension will be used in both of those. So we will keep it separate as x is horizontal and y is vertical. For this, again, initial distance, this is velocity over time. Remember we saw something similar, x equals v times t. So this is just a distance due to initial velocity. And this is going to be a distance, since you were multiplying it by time squared, we can actually look at it and go meters per second times second squared, and you get meters. So this is also a distance due to acceleration. So we're just adding three different distances together. And in the same way, acceleration times time is going to be a velocity. And so you're adding two different velocities together. And so when we are looking at a falling object, so the distance is in one direction, but it's going up or going down in this case. You'll have x equals x sub 0 plus v sub 0 t plus 1/2 gt squared, and v equals v sub 0 plus gt, or a equals g, which is 9.8 meters per second squared. This is basically saying that when you're dealing with an object falling, you use your acceleration as gravity. So acceleration could be anything, but if it's falling, it's just going to be gravity. So if this is horizontal motion with a car, acceleration could be constant at anything else. But if it's falling, this is your constant acceleration. The reason I have plus or minus down here, I can put plus or minus down here, is because depending on how we want to look at it, we can say down is negative, so up is positive, or we can actually say that down is positive. It depends on how we want to look at it. Why would we say down is positive if traditionally we make down negative? Well, if an object is falling and we want to know how far, do we really care that it's negative? We know it's falling. So we can make this positive and look at how far it falls. Why would we say it's negative? Well, if we toss this ball up in the air, and we may want our velocity there to be a positive direction going up, then we have to make the negative direction going down. Okay, so it kind of depends on how we want to look at it. Best thing to do is define it right at the beginning. That way you know which is positive, which is negative. That sets up your gravity. So you know what? I'm going to do a problem with this because I don't know if I really have. I have a few problems, but I'm going to do one specifically for this. That's not in your notes. Before I keep going. So let's say we tossed a ball straight up, and this ball we tossed at a velocity of 2 meters per second. And we want to know how high it goes. And then it's going to come down. When it comes down, we're going to miss it, and it's going to fall off a cliff. That's just say only 5 meters high. So it's not a high cliff. Which, I mean, what is that? About maybe 15 feet. So it's not too high, but we're tossing it up and then it's falling down. We want to know a couple things. Maybe we want to know how high it goes. Maybe we want to know how long will it take to land. Maybe we want to know what speed will it hit the ground. Okay, so if we look at this, tossing it up, one important thing is at the very top, it's going to have a velocity that's equal to 0. So it starts out at initial velocity equal to 2 meters per second. Is going to come to a final velocity at the very top, which is going to be 0. So let's find how high it goes. Well, if the initial velocity, let's start with that equation. Initial velocity plus AT. If the initial velocity is going to be 2, and it's going to be a positive 2 because I'm going to call positive up here and negative down. So gravity in this case is going to be a negative 9.8 meters per second. So positive 2, final velocity is going to be 0, acceleration is going to be our negative gravity, so it'll be minus 9.8 times t. This will tell us how long it's going to take to reach the top of its peak. It's not going to be how long it's going to take to land, but just to reach the top. And so 9.8 t equals 2. So t equals 2 divided by 9.8. We get 0.204. Right, so that's going to be the time it takes, 0.2 of a second. Then we want to know how high. Well, let's switch over to our next equation. X equals x sub 0 plus v sub 0 t plus 1/2 at squared. Now, I've already mentioned that A is going to be negative 9.8, so I can write it this way. I'm going to call x sub 0 here equal to 0, because we want to know how high from where we threw it. So 0 plus 2t minus 1/2 gt squared. A lot of times we just write in g instead of 9.8. It's a lot easier, and then put in the calculator as 9.8. And that's going to be equal to x. So we'll solve this over. Actually, wait, hold on a second. We have the time. We'll add in the time. So 2 times 0.204 minus 1/2 9.8 times 0.204 squared. So 0.204 times 2 minus 0.5 times 9.8 times 0.204 squared. And it will be 0.204. Be how far? Hold on a second, Rachel. Right, so that's how far it's going to go up. And so now we have how high. It took both equations to figure that out. Okay, we can do it in one equation, which, I will mention here. We could do this equation here. Velocity squared equals the initial velocity squared plus 2 times acceleration times distance, which not dx. And then you can technically solve for x. I don't tend to use that a whole lot. I like to do it in just 2. It's just something I like to do, I think, because I actually get the time, and a lot of times that getting that time is helpful. But you can use it as well. Alright, so the next part of this is figuring out how long it's going to take to land. Now we can do this in a couple of ways. I can do this by just looking at from here to here. And I can even, at that point, make the time positive, or the acceleration positive. Or I can do it through the whole problem. You know what? I'm going to do it both ways. Let's do it through the whole problem first. What we know is that at this point, this is where x sub 0 equals 0. So we have this equation, x equals x sub 0 plus velocity t plus 1/2 gt at squared. I'll put in the gt later. So acceleration, I'm going to make it negative g. And what I'm going to say is x sub 0 equals 0. X is going to be a negative 5. So negative 5 equals 0 plus your initial velocity of 2 times time, which this is a different time because it's going the whole length, minus 1/2 gt squared. I could have also switched this and put the x sub 0 down here and made x sub 0 0, and then it ends up at 0. That's another way. Well, I'm sorry, x sub 0 were in 5 because 0 would have been down here, but it ends up at 0. That's another way of doing it. I'll draw that out in kind of a different picture. So if that's 5 meters, and it comes up and lands. So let's say x sub 0 equals 5, but this is your 0 mark, so x equals 0. What you end up with is the same thing we're going to end up with here, is I'm going to move that 5 over this side, so we get 0 equals 5 plus 2t minus 1/2 gt squared. And then I can solve this using quadratic equation, which will be -2 plus or minus square root 2 squared minus 4 times a -1/2 9.8 times 5 all over 2 times 1/2 -1/2 gt squared. Well, I'm sorry, not the t squared. I can't get away. Right. I also can put this in the calculator. So either way would work. So I do 5 plus 2x minus 0.5 times 9.8 x squared. That's another way you can solve this, and then you find it where it lands at the 0 mark. So second calc, it'll be 2 is your 0, so you just gotta move it close to that, left, then right, then enter again, and you get 1.2 for your time. And that'll be 1.23 seconds. The other way is we could have just found it this way, and you'll probably end up thinking this way is easier, is we're starting out here at 0, and we want to find the time it takes to get down here. We know how high it went, which was 0.204. So we know it's falling this distance here was 0.204. So it's falling 5.204. And as it falls, it's going to take time till it hits the ground. So we can call this negative, and we can call the final distance 0. Actually, I'm making this a lot harder than it needs to be. Let me write out the equation here. X equals x sub 0 plus v sub 0 t minus plus actually 1/2 at squared. So if we're going to call that 0, that's going to be how far it falls. We don't need a negative sign. It'd be 5.204. The initial velocity is going to start at 0 here. Don't worry about this initial velocity anymore. We're just looking at this section of it. So this is going to be 0t, and this will be 1/2 9.8 t squared. So it's going to fall, and this will allow us to determine the time it takes to fall. So we'll do 1/2 9.8 t squared equals 5.204. So 5, oops, let me clear it. And then solve for t. So times 2, divide by 9.8. And then we take the square root. Oops, clicked off the page, off the thing. Now you get 1.03. So time is equal to 1.03. That's that section. The overall time is equal to 1.03 plus 0.204, and so you end up with 1.234. So very close. I mean, I rounded here, so pretty much the same time, and will be the same time. I mean, we're just breaking it down into parts. This way will allow you to avoid quadratic formula, but that's not a problem to do that. Okay, so before I forget, I'm gonna probably start a new video here for the last few examples. But before I do that, I want to mention the last thing with this. If you are dropping something and there's no initial distance and no initial velocity, this whole equation boils down to just 1/2 at squared. And for that matter, if it's dropping, you know where acceleration is because it'd be gravity. And then the velocity equation with no initial velocity is just v equals at, right? Which makes this a lot easier to handle when you know these things are zero. So a lot of times we look at trying to set up equation problems where we make certain things equal to zero because it just makes it easier. Okay, so in the next video, I will go through the last few examples. One would be involving graphing. That shouldn't be as long of a video either. But I know if I get into this video is going to be extremely long. Plus, I think my wife's home, so I want to help her with groceries before that. All right, so I'll see you in the next video. Bye.